So these next derivatives are also what we're going to consider as defined derivatives. We're not going to justify these right now. We're just going to have these like basically on a formula sheet, and whenever we see these, we're going to apply these derivatives. So the first one is fairly special because this exponential function, e to the x, when we differentiate it, it just happens to be itself. And this is the only function that does this. And in general, exponential functions tend to regenerate themselves. So the rate of change of an exponential function is equivalent to the y-coordinate of that exponential function. Okay, this is very unique. Even when it's not base e, the derivative of a to the x tends to regenerate itself. And because it's not a base e, which is the perfect base, okay, we have to account for non-base e's with this extra log a. Okay. For the log function, we're going to differentiate it. It becomes 1 over x. Again, we're not going to justify this right now. I'm going to show you some graphs that kind of confirm that this is the case, but there's no proof of this. Okay, so this is just something that we're going to get to know. The derivative of log is 1 over x. Okay, so the log, when we do ln is base e. When we don't use base e, everything gets messed up. So we kind of really want base e. So when we use base a, we have to account for that 1 over x. We have to account for it with a divide by log a. Now easy way to remember this is when we differentiate exponents, we have to account for it with a times log a. When we differentiate the log, we have to account for the a with a divide by log a. Okay, but if we use base e, everything works out much nicer. So we want to use base e whenever possible. So let's apply these. Okay, so I have an exponential function here. That 2 has no effect on the exponent. Remember, the constants of multiplication there do not affect the differentiation. We have to keep track of them because it will affect the vertical expansion. But otherwise, we can just differentiate 3x. Okay, so the derivative of 3x is 3x itself. Okay, it just regenerates itself. But again, since it's not a base e, we need to just account for that with an extra log e. So the derivative function y prime is going to be 2 times 3 to the x log 3. Okay, if you want, you can bring the 2 log 3 together as one coefficient. And that's it. The exponential functions are nice and easy to differentiate. Okay, so there's a formula. Let's apply the log. Well, the log, when we differentiate log, again, the 3 is going to have no effect on this. So when I differentiate the log, I'm going to keep the 3. And the log function is 1 over x. Okay. But because of that non-base e, I just have to account for that with a divide by log of that base. Okay, so really it's easier just to kind of put it all into one denominator. So x log 2. And that's it. We're done. The derivative of log is 1 over x. Okay, now this one here, we do have some log properties. So instead of dealing with that extra log 2, this is what I'm going to do. I'm just going to use change of base. I can change any log into any base I want. So I'm going to change this into 3 base e of the argument divided by base e of the base. So there it is. The base ends up in the denominator. Now this is all a constant value here. So when I differentiate this, I'm just going to keep this as 3 over log 2. Okay, and then I'm going to differentiate, and I'll just color code this so that just stays all the same. I don't differentiate constants. And I'm going to differentiate this log x with 1 over x. Okay, well, if I take a look at these two expressions, they are exactly the same. So what I would recommend is, in log, since we have a change of base formula, let's use the change of base formula. Let's change it to base e right away, because base e's are much easier to work with. So that's my strategy. Now, if you don't use that strategy, that's perfectly fine. You get the same result, but it's probably easier if we just keep everything in base e. So here, this is already in base e, so I'm just going to apply my log. It's I just go to my, if I forget what it is, I just go to my formula sheet, and the derivative of log is 1 over x. Okay, the derivative sine is cos, and the derivative of cosecant is, well, I forget what that one is, so I'll go to my formula sheet. It's negative cosecant x cotan x. Okay, so there it is. There's my derivative, and this is nothing. I didn't do any slope formula or anything like that. I just went to a formula sheet and got these. Okay, now we did try to justify this a little bit, that these are in fact the derivatives. We have no real proof yet, but for now you're gonna have to take it. You're gonna have to have a little bit of faith and just say, well, this formula sheet says it's right. I'm gonna believe it's right for now. Okay, later on we'll do a little bit of proof of these and actually justify these. There is a set of videos here that we can trace out slope values of log and e to the x, and we can see that the slope values do actually trace out the functions that we are claiming the derivatives that are its derivatives.